Роман, Хельми, слышно меня?
Слышно.
Слышно, Оль.
Ром, проверь, пожалуйста, ссылку на YouTube новую.
Да, ссылка есть.
Отлично, посмотри, работает, идет стрим или нет.
Да.
Оль, меня так слышно, а то у меня
Отлично.
ноутбук не исправен, да?
Шикарно.
Хорошо,
Шикарно.
спасибо. Угу.
Да. Там небольшая задержка есть, кстати.
Это не важно. Меня интересует, идет стрим или нет. Идет?
Идет.
Все, значит, этот стрим живой. Тот почему-то не пошел, видимо, скорости не хватило. Супер. Хельми, ты можешь пока расшарить презентацию?
Хорошо, сейчас сделаю. У меня тут сложные системы технические. Сейчас сделаю. Сейчас.
Такая, Йорк.
Оль, я первая, да?
Ага. Yeah. Just try to share your presentation because you told us about the problems, technical problems with your computer. Because Zdeněk is not here yet.
One moment. Так, сейчас. Видно? One can see?
Yeah, yes.
Yes, видно.
Perfect. Very well.
У меня только иногда не переводятся почему-то, не перелистываются
это нужно
страницы.
выйти еще раз. Just run it again. No, it's you cannot kill it. Just run the presentation again. Hi, Laxman.
Hello, Olga.
No.
Yeah.
Just quit and then run the presentation again. Выйдите и войдите еще раз. Закройте презентацию, откройте.
Видите, вот здесь.
Надо перезапустить еще раз. Это бывает. Where is Zdeněk? He is the speaker.
Кстати, Оль, не спеши, у тебя, по моим часам, сейчас еще 53 минуты. Ты очень в прошлый раз раньше начала.
In English, Roma, in English.
Ну, это между собой.
Yeah, Heavy, try again. Try to run it again.
Why?
Because we couldn't see your presentation properly. There was this box which covered half of the presentation. Please try to run it again. Because we don't have Zdeněk yet.
Так.
Super. Now it works. Okay.
Thank you.
Yes.
I'm sorry, I have some technical problem with my notebook.
Yeah, Misha raised his hand. Misha, speak up. Yeah? Any questions? Helmi, is your cat meowing?
It's my cat.
Okay. Everything is fine, but I cannot see Zdeněk, who is the first speaker.
It's not time yet.
Yes, I know, but I'm a bit nervous. Maybe something he cannot join us or something.
Maybe he will return.
At previous section, people starts to watch a bit
later. I know because but speakers, all speakers were early.
Yes.
Oh, Zdeněk.
Oh, I am here.
Okay.
You know, we were
I'm sorry.
We were nervous, and Helmi was ready to cover the whole. If you are not here.
Yeah. I only renamed now this. Could you hear me?
Yes, very well.
Fine.
Very well.
Ah, Yana, I can see Yana.
And should I start or?
Just maybe 1 minute.
Yeah.
Don't you mind? You can just open your presentation and we'll wait just a couple of minutes and then you begin.
Já jsem chtěl na ten meeting. Share screen je, která to je? Aha, tady. Share.
Si vypni kameru, až to otevře. Počkej ještě.
Jak to já tady přehodím do toho?
Okay, it's time to begin.
You can see my screen, yes?
Yes, very well, very well.
It's not. Actually, the talk, the title is that it will be about temperature spectra in solar wind, but it will be a little more complex. Here's outline. I will start with some motivation, and I will spend a relatively long time with definition of temperature, what actually temperature is, and how it can be determined from experimental data. Then I will talk about relation of spectral slopes of thermal velocity and other parameters. I will talk about ion beta, anisotropy and other parameters. And I will, if I will have time, I will go even to conclusion. Here's the motivation. We published in 2016 a paper. The main principal figure from this paper is shown in the middle. And the main conclusion of this paper was, regarding the temperature, that the spectra of the temperature are most similar to the spectra of bulk speed. In 2018, there was a paper of Gogoberidze, and they argued that the temperature spectra should be similar to the density spectra, and that there is a problem that if you have some temperature anisotropy, you actually calculate some pseudo temperature or measure some pseudo temperature, and actually the real spectra of the temperature should be similar to density spectra. And for this reason, we looked at the problem in more detail, and what we would like to discuss is what the temperature actually is, what it is in multi-component plasma, and how it can be determined from the experimental data. It will be the first part of the talk. I will start with something like textbook, because if we will take the Maxwellian distribution, which is typical approximation, the temperature is the parameter of this distribution. In such a case, it is scalar, and if you would like to compute it, you can compute it as a second order moment of the distribution. If the distribution is non-Maxwellian, but isotropic, the second order moment is again scalar, and again it can be used as some measure of the internal energy. It means that it is some effective temperature. If the distribution is non-isotropic, the temperature becomes tensor, and scalar temperature is usually defined as the mean of the elements on the diagonal of the tensor matrix. If you have some preferred direction, actually in magnetized plasma it is magnetic field direction, and if the distribution is symmetric around it, you can define parallel perpendicular temperatures. But if you have more components, it becomes a problem. You can see on the left-hand side, you can see the measured distribution from Helios, and you can see proton population, proton beam population, alpha, and even alpha beam. Yeah? It's clear that all of them, because the temperature is about width of this fit, it is clear that we will have the problem with temperature in such a case. And how we can calculate it? You can calculate it as a moment. You expect that you have measured the full distribution, as here, again, this example of Helios data. And but if you will compute the second moment of such distribution, and you have several species here, as is shown in bottom, this temperature will also include the differential velocities of this species, and you will have relatively high temperature. You can fit the distribution. You can use fit with several populations, which was done here, and but the problem is how many species you have. For example, in this particular case, there is proton core, proton beam, and alphas. You have three populations. It means that you need for fit actually 18 free parameters, and it's a lot. That means it's a problem how this fit will converge. But still, if you will be successful, you can determine the parameters of all. But now return to the temperature. If you will fit the same distribution as I've shown before, if you as distribution of independent populations, each of them will exhibit larger perpendicular temperature than parallel temperature, because this is the direction of the magnetic field. But if you don't take into account the presence of several populations, say, like in this case, proton core and proton beam, and you will fit with one population, you will have much larger parallel temperature than the perpendicular temperature. And it can be demonstrated here. What I'm showing here is two ways of processing of wind data. Probably all of you already used sometimes wind data. And you know that what is public processing with one anisotropic proton population, and but there is another processing of the same data made by Ben Alterman, and they fit the distribution by two populations, core and beam. And you can see how the temperatures will, how the ratio of anisotropies in this case will look. If on the horizontal axis, you can see the ratio of abundance of, say, proton core and proton beam and proton core. And if the beam population is very small, you have the same temperatures. But if you have large population of the beam, you can have relatively big difference in temperature anisotropies. And then let us look how we are computing the temperature. We have measurement of Faraday cups on spectra R, and we measure these 3 points of distribution, and we compute the temperature, which is actually the derivative of this curve. And we checked that what we received is the trace temperature. That means now I am talking about trace temperature, and the analysis here shown here is made. We took all data from spectra R in the solar wind. We divided it into 20 minutes intervals. We have about 30,000 of such intervals. We computed fast Fourier transform, and then of many quantities, and then we computed median spectrum. You can see that the spectrum is well defined for all quantities, and then we fitted it by two straight lines, in three lines in case of density because of flattening of the spectra at the end of the inertial range, and the results, the slopes and breaks are here. You can show this table. You have complex analysis here in this table, yes, but the problem is that it is not too illustrative. For this reason, I will show some examples. It is how the slopes change with beta. It is in inertial range for all quantities, and you can see that if the beta is, say, intermediate, the slope in inertial range is less steep. It is steepest in kinetic range, and all these quantities we analyzed behave the same way with respect to beta. And now, because we started with temperature anisotropy, we can look at the temperature anisotropy. And again, we can see that all quantities behave with temperature anisotropy the same way. And we can look if there is no temperature anisotropy. It's isotropic plasma here in inertial range, and you can see that the temperature spectrum is the most similar to spectrum of perpendicular velocity. It's not true in the kinetic range, but we were talking about the inertial range. Again, you can see the comparison of temperature spectra, slope of temperature spectra and density spectra, and you can see that they are far away because this 1-to-1 is given by this green line, but you can see some similarity with perpendicular temperature. And the practically the last result is here. It is correlation of slopes in inertial range and in kinetic range with correlation of all slopes of all quantities with slope of thermal speed. And you can see the best correlation in inertial range is for perpendicular component of velocity. In kinetic range, everything is practically the same. It means the trends. It doesn't mean that the slopes are the same. It's correlation. Here is maybe you can read it if you would like, because actually I already.
No. You have 2 minutes. No problem. We would like to hear this from you. Of course, we can read.
And maybe I can go to the conclusion. If we, and the main conclusion is, if we analyze the median spectra, usually if you have different cases, the spectra can be very different, yes? But if you look at the median spectra, usually they are very well defined, there is no noise, and you can determine very well slopes and breaks of the spectra. And regarding the analysis, the spectral slopes of all analyzed quantity vary with changes of background parameters in a similar ways. Values of slopes of perpendicular component of the velocity are similar to those of the thermal speed in the inertial range. And in the kinetic range, practically all slopes, slopes of all quantities vary very similarly. That means that the conclusion, we started with this discussion of paper of Shafrankova and colleagues, and the main conclusion here is that the conclusions in this paper are right, that the velocity and temperature spectra are most similar among other quantities. Thank you.
Thank you. Very interesting. This is something fundamental. Very good. Questions, please, and comments. Can you send us a link for your paper?
No,
and, can you share the link?
Link?
You quoted the paper and you said it was published. But
you mean the paper on this old paper? Because
yes.
This is not already published. Yes.
No. I'm talking
Probably
about
I
the
will
old
try
one.
to copy it to chat.
Okay.
Because
take
I
your
should
time.
find first.
Not
I
right
should
now.
find this. Yes.
Okay. Bravo. Thank you so much. And the next speaker is Helmi.
I'm sorry, I have one question.
Yes, Masha.
Zdeněk, hello. I have one question about that all these results. It's concerned of all solar wind condition, or only some specific for slow, quiet solar wind, or something like this?
Oh, no. This is for all solar wind conditions. The only condition for selection of spectra are data or that the spectra is in the solar wind. Even there will be maybe some spectra from maybe some weak forest shock or things like that. Actually, the only condition was that the spectra is in the solar wind.
And the situation is the same for all conditions. For example, for slow stream and for fast stream.
No. You can look if maybe I will start the share screen again, and I will show you this table. Yeah, you can see what we analyze. We analyze temperature anisotropy, level of fluctuations, what seems to be very principal is collisional age. Actually, it divides slow and fast wind in some sense. Beta, which is usually taken as a very important factor, we didn't find as so important, and we did other analysis. Probably these two, I think, are most important for formation of the spectra. Usually, if you have very high standard deviation, which is very high level of fluctuations, you have usually steeper slopes, and for low standard deviation, you have shallow spectra, and so. And but of course, there is no problem. We can because everything is already computed. We can sort data according to say solar wind speed. Yeah, but we didn't it.
Okay, thank you.
Thank you. Any other questions? Thank you, Zdeněk, again. Helmi, please share your screen.
Thank you.
No, to jest.
Sorry. Good afternoon. My talk is about universal scaling on thin current sheets in space plasma. This is a list of authors of this work. Sorry. Thin current sheets with thicknesses about proton gyroradio appear in magnetopoles and magnetotails of planets as a result of the solar wind interaction with the intrinsic planetary magnetic fields. In the solar wind and solar corona, they appear at boundaries between different magnetic fluxes, plasma flows near X-line reconnection regions. But that is a question, how is the different dynamics in thin current sheets and in thick current sheet with magnetized particles? In thick current sheets with all magnetized particles and currents that are supported by pressure gradients, the particle dynamics is different with thin current sheets. So electrons are fully magnetized, but ions can be demagnetized in the neutral plane and go along the so-called meandering serpentine-like orbits in the normal magnetic field in the neutral plane. The motion is governed by the parameter of quasi-adiabaticity introduced in the famous paper by Buchner and Zeliony. This parameter of quasi-adiabaticity is less than 1 for ions and more than 1 for electrons. Also, during the motion of ions in thin current sheet, the approximate integral of motion, Iz, is conserved. And this is named the quasi-adiabatic approach. Cross-tail current in thin current sheet is supported by the average duration of meandering quasi-adiabatic ions and by electron drift currents. And in the frame of the model, one can describe the thin current sheet in a frame of the hybrid approach, that is quasi-adiabatic approach for ions moving along meandering orbits in the neutral planes, and standard guiding center approximation or MHD approximation for electrons which are magnetized. But unfortunately, the scale-less MHD approximation does not allow to estimate the characteristic thickness of electron current. In our previous work and works of other authors, it was supposed that current sheet thickness, electron current sheet thickness, is about the Gira radii of electrons. It's not right. The aim of our work is to investigate the self-consistent structure of the embedded electron current and to estimate its transversal scale. Electron current sheet thickness is very important in space plasma processes, for example, for magnetic reconnection. The smaller current sheet thickness, the larger amount of free energy can be reserved in such thin current sheet. Thus, current sheet stability and explosive release of energy during reconnection processes depend on current sheet structure and the particle dynamics in it. Therefore, we developed a simple analytical model which demonstrated us the universal character of the nonlinear magnetic field profile in the very center of thin current sheet. We supposed that thin current sheet consists from two embedded sheets. The external sheet is supported by quasi-adiabatic protons at meandering orbits, and its shape can be used in the prescribed form. The inner sheet, that is super thin electron current sheet, is supported by the drift motion of magnetized electrons. So the basic 1D configuration of thin current sheet has the form in the simplest case of shearless configuration consisting from two components, the tangential px component in GSM system of reference, and Bn or Bz component, the normal magnetic field. In the presence of the magnetic shear, one can take into account three component and also By component, which is not equal to 0. What input parameters that we have in the model? The normal magnetic field Bn, plasma density n, electron and proton temperatures. These parameters can determine two important spatial scales, the ion inertial length, delta y, and the ion Gira radius in the field Bn. Also, one can introduce the dimensionless parameter eta, which is the ratio of the ion inertial length divided to ion Gira radius in the field Bn. And we have shown later that this determines the embedded thin current sheet structure. So we use the Ampere equation, which relates current density of ions and electrons with the magnetic field. And here the electron current can be described in a frame of guiding center approximation. And I should say that the maximum intensity of electron current is reached, which is reached near the neutral plane, is the curvature current, which is much greater than the current due to gradient of electron pressure. So we take into account only curvature current of electrons in the neutral plane. Using the marginal Fairhouse stability condition in thin current sheet proposed by Burkhardt earlier, one can simplify the expression for the current of electrons, and the Ampere equation finally has the differential form. And in dimensionless variables, the same expression has the form as it I present. Oh, sorry, this is my cat. This is the differential form, which include the derivative of the magnetic field on the cross sheet coordinate z, and this equation can be integrated. The integration of right and left hand sides give the following analytical expression, where At the right-hand side, one can see the shape of current density of ions, which can be considered as a step function, sometimes as a bell-shaped function, but the choice of the shape does not change the results of this model. And the final equation describing the embedded current sheet in a dimensionless form is presented here. This equation has asymptotic solutions. The asymptotic solution in the region where electrons are dominated population, B, the tangential component of the magnetic field here is proportional to the z coordinate in the power 1/3. Far from this region, this is a region where ions are dominated, magnetic field is proportional as the linear function. And here one can see the shape of magnetic field lines, which have such specific form. And using these approximations, one can do some estimate of parameters of this system. For example, we have estimated the parameter of embedding, which is the ratio of magnetic fields at the edges of electron sheet and of ion sheet. It is proportional to the ion inertial length divided to the ion radius in the field Bn. And I should say that it is the universal estimate for the embedding thin current sheet parameters. Also, we estimated the characteristic scale of the electron embedded sheet, which is proportional to the square of the inertial ion length divided to the ion radius in the field Bn. And what happens if we take into account the magnetic shear in the system? Recently, we have generalized our model to the case of magnetic shear. By component here is constant and not equal to 0. And in this configuration, magnetic field lines are inclined to the angle alpha, relatively the vertical axis z. So the tangents and cosinus of angle alpha can be expressed from the magnetic components By and Bz or Bn. We have received from Ampere equation analogically the universal equation which describe the shape of magnetic field in thin current sheet, which contains two embedded current sheets of electrons and ions. And for asymptotics at B much less than 1, we receive the same universal asymptotics, which does not depend on the presence of the shear and details of equilibrium. Our colleague Elena Grigorenko has done a great work to compare and to find magnetic field observations in the Martian magnetotail. She generalized the set of 43 current sheets, current crossings in the magnetotail. And she found the cases then electron sheets were very clearly seen in the profiles of current sheet crossing. So the observation of probability as a function of a power index A is presented here, and one can see that power index A is about 0.33. That is, it is very close to our theoretical prediction. Our conclusions. The new theoretical approach to the analysis of thin current sheet equilibria revealed the nonlinear structure of the embedded electron sheet and allowed estimating its thickness as well as calculate parameters of current sheet configuration. Magnetic field observations demonstrate very good correspondence of our result concerning nonlinear magnetic profile, B proportional to the Z in the power 1/3 in the very center of current sheet configurations. While the half thickness of ion external sublayer is estimated as the ion inertial length, the electron layer in thin current sheet is scaled as proportional to the square of the ion inertial length divided to the ion radius in the field Bn. So the obtained scaling is universal for collisionless space plasma and consistent with observations in the Martian magnetotail. Thank you very much for your attention.
Thank you, Helmi. It's very interesting because it can be used in simulations. Very important result. Thank you. Any questions?
Thank you.
Please. Okay, then if someone wants to ask anything, just contact Helmi. Well, so it looks like I'm the next speaker, but I need someone to run the session because I don't see the timer here. Laxman, you are the after me. Can you do this for me? Just stop me at, when I have 2 minutes left, okay?
Okay.
Okay, then
Yeah.
I start sharing my screen. So, well, this morning we had, can you see this properly? It's better to do this. Okay. This morning, Timothy Sagitov gave us a talk about how we created a new, and I would say the only database of current shifts in the solar wind. The point is, the motivation was like this. There are several methods of identification of current shifts in the solar wind. And all these methods, they don't have outcome as a database. All databases that people have is, for example, the database of current shift reconnection exhausts compiled by Jack Gosling. But as you can see, it's kind of random. And the same situation about, for example, about the MMS. Okay, there are a lot of current shifts in the solar wind, but they indicate only interesting cases. And every observer who wants to understand how current shifts behave in the solar wind, what are the main features, they should compile their own lists of current shifts. So we created this database, and everyone can just reach this via our Izmeran website. If you don't remember this link, just come to the main page of Izmeran and come to data and observations. You will find our database there. And this is just a reminder from the morning session if someone didn't attend. The point is that we use not only variations in the magnetic field as most of automatic methods of current sheet identification do. Well, we use not only this, we use it and this, and but we use also plasma parameters. We use the variations in plasma beta, because most of current shifts, not all, but most of current shifts in the solar wind are high beta structures. And we use the decrease, statistically confirmed decrease in the ratio of alpha speed to the ordinary speed of the plasma flow. So the number of current sheets per day, this is smoothed. Actually, sometimes we have even more. Well, it's about several thousands current sheets per day. What does it mean? Why we have so many current sheets per day? Of course, there are some variations, no obvious solar cycle dependence. This is important. And why we are talking about such big values? We are talking about such big values because current sheets in the solar wind is not only the heliospheric current sheet, which can reconnect in this way. Actually, it's not a plain structure. Recent observations and, of course, simulations show that this is something about magnetic reconnection and creation a lot of secondary current sheets and plasmoids around the heliospheric current sheet and similarly strong current sheets. So the point is that every time when they cross, when they approach strong current sheets formed, for example, they can have a solar origin, as we know, and they can be at edges of streams or within the streams and flows, high-speed streams and flows from the sun. Then we have this process of creation of secondary structures, of coherent structures, which this is the way actually to create turbulence. This is one of types of the turbulence, but there is the other type. If we are too far from strong current sheets, we are still in the medium which is filled with current sheets because of course, turbulence. This kind of simulations were shown in the morning, not in the morning, in the afternoon, in the first session. But this is just a reminder that actually every time the solar wind is not just something flowing like water. It's these processes of mixing, of creation of turbulence, they work from the corona. Actually, they begin there and they continue, of course, in the solar wind at 1 AU. Well, so that's why we have so many current sheets per day. And then we come to statistics. If we analyze properties of current sheets with 1 second resolution, then we can see typical properties, expected properties from other studies. Yes, people have shown that plasma beta increases, yeah? The density increases, and often speed to speed ratio decreases exactly at the current sheets. And this is not a surprise because it was shown before. But look at these numbers. We are talking about millions of current sheets. We are talking about millions of events seconds without current sheets and events with current sheets. This is the first comprehensive study, the statistical study of properties of current sheets in the solar wind. If we look at other scales at hourly average data, we actually check not the properties of the current sheets themselves, but properties of the surrounding solar wind. And these histograms are dramatically different from those that we have seen just a second ago. Look, we have decreased plasma beta, decreased density, increased ratio of alpha speed to speed, solar wind speed, and the solar wind strengths, IMF strength increases, speed increases, and temperature increases. This is something different. Let's just compare. This is 1 second resolution and this is 1 hour resolution. Dramatically different. Which means that we have to be very careful when we analyze processes in the solar wind, actually any processes, but especially current shifts. Because at different time scales, the solar wind looks absolutely differently, and properties of current shifts look absolutely differently. Then the next question, as you can see from here, the speed and temperature is high in the surrounding solar wind, which contains current shifts. So it was expected, and we found this result, that these peaks actually, they are determined by increased speed and temperature. The temperature plays, it does good job actually, 10 times more good than in comparison with speed. And this is the best fit parameter. Don't ask me how I did it. This is my know-how. I have, it's too long to explain how I found this parameter, but just compare the correlation with the most well-correlated parameter with the number of current shifts per day is 0.7 here for this period and 0.6 for this period. But the best fit parameter correlates with the number of current shifts per day much better. It's 0.8, you see? So we found it. The number of current shifts per day is determined by variations of the kinetic and thermal energy density of the solar wind. This is the first result of this kind. Nobody did it before. And then the question appears, what is this? Does the solar wind determines, okay, we have some flow, and because of its temperature and the speed, more current shifts appears, or the opposite. There are a lot of theoretical works about the heating of the solar wind by current shifts. So the question is open, and discussion is open. Nobody knows. For example, I think that the solar wind determines the rules, but theoreticians may argue. Well, if we look at key studies, it's like this. Indeed, the increase in the number of current shifts per day is obvious in stream interaction regions and ICMEs. That's why I was so interested in the Alexandra Khokhlachev's and Maria Ryazant's results about the alpha particles in the solar wind, because they found that actually number of alpha particles decreases in ICME shifts and SIR-CIRs. This is something, for me, this is something about current shifts, because we know that around the heliospheric current shift, the number of alpha particles always decreases, always. This is the rule. And let me just, for those who is not familiar with these stream interaction regions and ICMEs, just a short reminder. You see the sun from above, and here this sphere, this is about 2.5 U. So these are planets and different spacecraft, and these rotating flows are actually SIR, stream interaction regions, because they are formed by high-speed coronal hole flows. And these bubbles are ICMEs. ICME sheaths, actually, the most dense and turbulent region of ICME. So no surprises. This result is confirmed by building this histogram. We are talking about our resolution, and this is our resolution, 1 hour resolution, and we have again a lot of current shifts for this period, analyzed for this period, and we can see that inside ICV sheaths as well as inside stream interaction regions, they have increased number of current sheets per hour and per day as well. And this is something different. Here there is superposed epoch analysis for the same period. And as you can see, there is some difference. If you look closer, we can say that a peak of current sheet number per hour occurs exactly at in the beginning of ICV near the shock, but it's still high inside the sheath, ICV sheath. And when we talk about rotating interaction regions or stream interaction regions, the peak occurs at stream interface. And here already we are inside the kernel hole flow, but still the number of current sheets is big. There are no theoretical explanations yet for this, but we can see some differences and similarities. So the conclusions are like this. We created a new database, open access database of current sheets at one EU, which allows everyone to just come, take the data, compare, and have these statistics. And this is very good for observers because we don't have this headache again where to find this data. And 1 second resolution histograms, they compared with the prior results, they show the same. But now we see what happens in the solar wind, which contains current sheets. We see that actually number of current sheets per day is determined by the kinetic energy density and the thermal energy density sum. And what is interesting, the thermal part dominates. That was something unexpected for me. Well, the maximum of current sheet daily rate again occurs in turbulent ICV sheets and SIRs. These are new results, not yet these are unpublished. And but we have this archive.org paper, which will be updated next week, and you will see the final, I hope, final version of this paper, and I hope it will be published soon. Well, and I would like to show you the papers, not show, but kind of advertise the papers published by our team, a big team actually, and these are big reviews about current sheets, plasmoid, flux ropes in the heliosphere. You are welcome to come to the research gate, and there is open access to these papers. And I also invite everyone to contribute to our special issue, which will be published in Universe. This is actually good and raising journal, which publishes very fast. 1 month and your paper is published. I guarantee that it will be very quick, and it will be published on the come first, have your paper published first basis. Thank you very much. Thank you.
Okay, thank you, Olga. It's very interesting talk. Yeah, you are on time. So, is there any question for Olga? Just 1, 2 questions.
Maybe I have one question.
Yes, Zdeněk.
Yeah. Did you think about the relation between frequency spectra or power spectral densities, for example, of magnetic field, and the occurrence rate of current sheets? Yes, because our feeling is that the current sheets are natural part and actually product of the turbulence in the solar wind. Because if you have frozen conditions, the magnetic field is carried by vortices in plasma and create current sheets. It is seen in many simulations.
Yes, exactly. It's exactly what I showed before here and here. It's you're absolutely right. And yes, we are going to do this here and here. These are two different types of turbulence, but yes, we are talking about the same. Good questions, because we didn't do this, but we have these plans. With I hope to do this with Maria Rizantsov's team and Yuri Yermolayev team. They have something, I think we have a lot of results to be compared, and in particular, this building of this spectra. Yes, yeah, right, absolutely. Thank you.
So may I ask you another question?
Yes, of course.
You said, okay, the maximum number of current sheets you had in the turbulent region, which I think, yeah, I mean, this we have seen in simulations, as you pointed out many, many times. The question, though, is, does the current sheet itself create turbulence?
Of course, of course, of course.
So you have two effects. The turbulence is created by the solar wind itself, but in addition, you have the turbulence created by the current sheet.
Yes. That's the point. And this is an interesting question. When I showed this result, when I have just obtained when we obtained this result about increased number of current sheets in turbulent regions, it on the one hand itself, on the other hand, this is the question of the duck and the egg. Who was
the hen and an egg question? Yes.
Mm-hmm. And yes, there is a lot of work about this for everyone, for both theorists and observationists. Yeah, correct. That was a very good question. You're right. Thank you. Okay, Laxman.
Yeah.
Are you ready?
Yes. So my turn, right? Okay. Okay, so do you see my slides?
Yes, yes.
Okay. Okay. Hello, everyone. Yeah. Okay. So I'm going to talk about the local particle acceleration in the supersonic solar wind. And these are the my collaborators. To begin with this talk, I would like to start with this ending model, which shows the this kind of structures in the solar wind plasma. And this is the condition of a disturbed condition, and this is very disturbed condition. In this case, we can see complicated steam-steam interaction, and which produces complicated structures or profile of this Hillsbury current sheet indicated by this white line. So making this kind of profiles, it makes cavity, and within that cavity we will see lots of small scale magnetic islands. So and that is responsible for particle acceleration, and which is different from the classical theory such as DSA. And because of that thing, particles are locally accelerated. So in this story, I will talk about this local particle acceleration. So in this cartoon, yeah, as we see here in a panel D, that close to the SCS.
Just a moment, Laxman, just a moment. Can you hide the panel? Stop sharing panel. Just click hide.
Oh, okay.
Yes.
Okay.
Super.
Okay. Thank you.
Thank you.
Okay. Thank you. Yeah. So yeah, here we see like close to the SCS, there are lots of magnetic islands here, and the this yellow diamond showing the two islands are reconnecting here. So stochastically reconnecting here, and due to these processes, particles are accelerated here. And in panel B, we see two kind of structure here, CIR and SES, and within this region, there are lots of islands here, and that also energizes charged particles. And here, panel C showing the spacecraft crossing CIR, HPS, and small scale island here, showing this structure here. So I will discuss this later in event 3. So islands. So what is small scale magnetic islands or flux rope? These are the coherent quasi 2D nonlinear structure, and these are formed due to multiple X-line magnetic connection. And if the hemispheric current sheet is very disturbed, then that also generates small scale magnetic islands. And several theories and simulation have shown that reconnection associated with merging and contracting magnetic islands energize charged particles. And this plot shows the observational evidence of small scale magnetic islands at 1 AU. It is taken from Jen and Hu 2018, and it also shows that the small scale magnetic islands depend on the solar cycle here. And there are several duration time scale in minutes here, from 9 minutes to 360 minutes duration. Small scale flux ropes here, and this panel shows the it is from Khabarova and Zhang 2017. It shows that, okay, so this is the reconnection exhaust, and in the downstream of the reconnection exhaust, we see a flux amplification here, showing that, okay, there is a particle acceleration here. So this kind of results suggesting that the particles can be accelerated locally, and which are not from the solar origin. So in my talk, I will discuss this thing here. So, okay, so if we think in terms of theoretical perspectives, then there are several postulates about the particle acceleration, such as first order Fermi acceleration and second order Fermi acceleration. So in this panel, in this plot taken from Luru et al. 2016, here this is single island, and here island can contract here, and when island contracts, it energizes charged particles. And in this case, two islands are merging here, like as shown here. When they merge each other, and it forms a single island, and during this process, it also energizes charged particle here, such as shown in this plot here. When two islands merge here, induced electric field generates here near the X point here, and that energizes charged particles. So from the theoretical perspectives, all these processes energize charged particles, and Zhang et al. 2014 included all these acceleration mechanism and derived a kinetic transport theory shown here. And in this case, it also has this induced electric field effect and contacting effect and merging effect here. And here, then what happens when magnetic islands contact? So in this case, particle gain energy in the parallel and perpendicular direction. And in the case of merging, particle gain energy in the parallel direction, but in the perpendicular direction, it loses energy here. So this kind of gyro phase transfer equation can describe the particle acceleration. And this is a very complicated equation. It can be simplified by neglecting by assuming the incompressible flow, such as making this divergence of U 0 and neglecting the second order form here. So when you do that, then it can be simplified and it can be derived this kind of analytical solution here. And it has several parameters here shown here, tau C, characteristic island contaction time, and several parameters are shown here. And if we input the values of this parameter, then we can calculate particle acceleration from the theoretical point of view. And if the general solution of this equation is just shown here. Okay, so this is the reconnection exhaust or the injection position here. It is normalized here, so 1 here. So in the downstream, the normalized this flux enhances here, and it becomes a peak value here, and then it decreases here. And so in downstream, it happens that the particles are attracted and diffuses, but in upstream side, particles only diffuses against the flow. This curve decreases exponentially here in the upstream region here. And this panel shows the just analytical solution of that equation. So here it just shows the power law here, and in a different case like a tau d over tau c2 and tau d over tau c 0.2. So when it is 0.2, then this spectrum is very steep here compared to this case here. So in this analytical solution, the second order Fermi acceleration is not included. So later, Luru ETL 2019 derive the transfer equation or analytical solution for both cases, first order Fermi acceleration and second order Fermi acceleration. So if we compare, if we see two cases here, the normalized flux as a function of distance, in both cases they look similar here. But if we look this normalized flux as a function of momentum here, they look different here. So in the case of first order Fermi acceleration, in the low energy side, they roll over here, which we do not see in the second order Fermi acceleration. So this mechanism can distinguish between first order Fermi acceleration and second order Fermi acceleration. So this is from the theoretical. So now I discussed this from the theoretical point of view. So now I go to the observation here. In my study, I consider three events. This is the first event observed on 2000 October 3 to 4, and it is originally found by Gosling ETL 2005. And Gosling found that here is a very strong reconnection current sheet here, found by Gosling, and shown by this this angle becoming from positive to negative here, the phi angle. And when Gosling suggested this phenomena and said that there is no particle acceleration associated with this reconnection exist here, and later Khabarova and Zhang 2017 revisited this event and suggested that there can be particle acceleration here, and why Gosling 2005 didn't find the particle acceleration is because they assumed the single page type reconnection. And in this panel, we see that, okay, so this is the shock and this is the seat region here. And Gosling found this current seat at the boundary of the ICME. So when spacecraft cross this region here, now spacecraft becomes or locates in the main body of ICME, and there we can see a particle acceleration here. And Khabarova and Zhang 2017 argued that this energization is due to the local particle acceleration, and instead of only a single current seat, there can be lots of current seats here shown by the vertical red lines, and it is identified by at least one of the magnetic field component is 0. And we also see that when spacecraft is located in the main body of ICME, it crosses the closed field lines indicated by this phi angle and then theta angle, going from positive to negative and negative to positive, and we can also see here. And next event is also found by Gosling and found 2013 here. And then and here, and similar to previous event, we can also see lots of current seats here, and this event is discussed in detail in Khabarova and Zhang 2017. So I do not discuss now here. If you are interested, you can see Khabarova and Zhang 2017. We use this observation result, and we compare with theory here. And in this case, we can also see this is the pitch angle distribution, and we can also see that when there is a current seat, there is a two steps of the pitch angle distribution here. So from this pitch angle, we can also identify that. And this is the third event, and then found by Gosling ETL 2006, and they found this event to find a strong page type of current seat here. And this is the event where a spacecraft crosses small island region, helispheric plasma sheet, and CIR here. And this is the plot of the particle acceleration here, intensity and flux here. And we see that in both regions, there is a enhancement in the particle acceleration here. And as suggested by Khabarova and Zhang 2017, this is also due to the local particle acceleration, and which is not due to the solar origin, and which we can see from this pitch angle distribution plot here. So for 273 eV, and there is a we can see the pitch angle distribution is dependent on this helispheric plasma sheet or small scale island crossing here. But if this is a very large energy, there is no dependent here. So this very large is from the solar origin. This large energy is from the solar origin, and this is not from the solar origin. It is due to the local particle acceleration here. So this is the case for that thing here. Yeah. So okay. So now I show the comparison of this theory and observation results here, and then here we compare theory and observation. The solid is from the theory, and then the dashed curve is from the observation. And different colors show different energy channel shown here. And we see that this is event 1, and we see here that the theory and observation matches a little bit far from the downstream region, downstream from this injection position, and close to the injection position. The theory and observation, they are a little different, is because the theory assumes that magnetic islands are fully developed, but it may be in the observation, which we do not see here. It also depends on the plasma condition here. For example, in this case, event 2, and here we see that just after reconnection, the observed flux amplification just starts to increase here just after this injection position here. But in this case, it is not. So it also depends on the plasma condition here. And in event 3, we also see the similar thing, that the particle doesn't increase, the particle doesn't energize until certain distance here, and after that it energizes. But although the theory and observation show a similar trend here, this is the normalized flux amplification, and yeah, it's larger than 1 here. And this is the intensity plot for each case. We compare theory and observation. The solid is the theory, and this dotted is the observation. And the kind curve is at the injection position here, and others are at several distances shown here from the injection position. And what we find is that at the injection position, the spectrum is very steep here. For this case, for here we see that the index is close to -2.5, and if we go a little bit far downstream, and we see that this index increases here, and it means that the spectrum gets flattening here with increasing distance. We found this in every event here. With increasing distance, the spectrum becomes flattening here. And this is at 1 AU, and we can also use similar theory at several distances, such as shown in this slide here. It is from Ulysses observation taken from Zhao et al. 2018, and this is from Ulysses observation. The first panel is particle intensity data, and the second panel is magnetic field components, and third is velocity and temperature, and then this panel D is density, and this is plasma beta here. So here this is the shock position here, shown by this vertical dashed line. And in the downstream, we see the enhancement in the particle intensity here, and there are several vertical shaded area. These are the flux ropes found by GS reconstruction technique, and there are almost 31 magnetic flux rope structure here. And we can also compare this with theory, and if we do that, it is found that there is a very nice agreement between theory and observation here, and here, and also similar here. And if we look in this panel, we see that if it is low energy, the particles do not energize until certain distance here. But if we look large energy here, they energize here within close to the this reconnection position here. Yeah, so and we also see here that the peak of the particle intensity behind the shock, and this is not due to the DRC, and also and also it shows that the increase in particle flux amplification factor increases with energy here, and this is at 5 AU, and similar things can also be studied like along the ST hemispheric transition shock position here, and this results also also shows that the this energization is associated with reconnection here, and this the solid is the theory, and the this other plot is from observation here, and there are 9 energy channel here, and it shows that there is a good agreement between theory and observation here, and here it shows that the amplification factor is largest like 2 times for energy range 1.8 to 2.2 MeV, and the amplification factor is 4 times larger for energy 15.3 to 17.9 MeV, and also this also shows that the flux amplification factor is ascending order with energy. So okay, so this is my last slide here. In this talk, I showed that the both observed and theoretical flux amplification are larger than 1 downstream of the injection position, and which indicates the particle acceleration, and that particle acceleration is due to locally generated magnetic islands. And then I also showed that the flux amplification comparison between theory and observation, and that shows that the flux amplification factor increases with energy. So for if there is a large energy, then we also get a large amplification factor, and if there is a minimum energy, then we get minimum amplification factor. But in some cases, we may not see that kind of this kind of mechanism here. In some cases, we may see reverse, but that is on maybe that needs to be studied. And then in this talk, I show 3 events. 2 of them are within ICME, and 1 is associated with SES crossing. And then this work found that if it is associated with SES crossing, then the flux amplification is smaller than if it is within the ICME. But of course, we also need to study more on this to make a valid conclusion. And here we found that the spectra of the slope varies between -1 to 2.5, and I also showed that the from the Ulysses observation that the there is also a locally accelerated mechanism happens near 5 AU, and also the observation evidence in the post hemispheric transition shock region, which supports particle acceleration by magnetic reconnection related processes associated with magnetic flux ropes. Yeah, thank you.
Thank you, Laxman.
So let me ask you a question. Your first point here, when you say, okay, it's downstream, can you show me again? And then you say automatically it's associated with reconnection. Did you ever prove that you see reconnection signatures?
Yeah. So as I showed in the okay. So okay. I also share the slides here. Yeah. So yeah, as we showed in the yeah here, there are yeah. So there are signature of reconnection here, and then here the magnetic field component goes from positive to negative here. So crossing 0 here, and
it's not a connection. Laxman, excuse me. It's just crossings. We are talking about it. Yes, there are signatures as a co-author that paper. I can say yes. We identified this with the Gangli's method, and yes, and then even simple patchy reconnection, it's always something like increased temperature for seconds, increased velocity for seconds. All these features, they are observed at the strongest current shifts within this fragmented ICME. Some of them were identified by Jack Gosling, and some of them just we did. Yes.
Okay.
So
Okay.
the answer is yes. But may I just comment, because we have 5 more minutes, again, as from the point of view of the observer. What Laxman did in his, I think, great work, he tried to explain that not only diffusive shock acceleration may be the mechanism which accelerates particles locally in the solar wind, but sometimes it's a combination of diffusive shock acceleration and the presence of this, we can say, turbulence or magnetic reconnection associated processes, as we discussed during the first session. So it's always a kind of competition between different mechanisms of particle acceleration, and together they work very well. But what Laxman showed, that in some events, in some cases, not always, but in some cases, it's very strange, but it seems that acceleration by dynamical process in magnetic islands, as predicted by Gary Zank and also Laxman and Cobos-Leroux, it works better than diffusive shock acceleration, and nobody noticed.
Yeah, it's a contributing factor, I agree, but I see hands here. Thank you.
And just one correction, Laxman, you said it was a kind of just not mistake, but correctly, you said that in the case of stream interaction region, rotating interaction region, possibly some particles, they came from the sun. No. In the case of the rotating interaction region, particles can be accelerated at shocks, which are formed far from the Earth, at 2-3 AU. So they basically come back to the Earth from that side, not from the sun. It was just, yes.
Yeah. So in this case, we use the data from LEMS 30, and that is pointing to the sun, right? So we do not see that kind of, for instance, if we use that LEMS 120, which is pointing towards Earth, so that can be contaminated by large spike due to reflected ion.
Yes, I understand, but some people may think that you are talking about actually ICMEs, not CIRs, and about this technical stuff. Okay, thank you. Thank you very much.
Okay.
Well, questions? Valentina.
Yes, I have a question, Laxman. Is he still available, or he's gone? Simulations show that the merging islands not always accelerate. They act sometimes oppositely, they decelerate. So I'm not so optimistic that in all your cases you will have acceleration, despite we did evaluation in the paper here in Jarkova 2020 of your methods, which Harry suggested, and we indeed agree with you that main acceleration of electrons comes from the curvature of magnetic field, because we see electrons in peak, they go in around the shell of the magnetic island. They follow the shell, so but accelerate in each x null point. So this is correct. The only question is that pay attention that not all merging islands would accelerate. Maybe it will be some different process. So you need to look at this more carefully in the future, in kind of thing.
Okay. Yeah. Thank you. Yeah.
Yes, of course. Actually, it not always seen, even if you have magnetic islands. No, not every time. This.
I agree that if we just imagine a magnetic island, and and some magnetic island can contract, some do not contract. And in the case of contraction, it energizes, but if it is not contracted, then if it expands, then in that case, particle may lose energy. So yeah, this kind of phenomena can happen.
Yeah.
But you know what? I can even show you how it looks like statistically, because I don't remember, maybe a week after this paper too, the first author was published Leroux. And if you allow me, because we have three more minutes, may I?
Yeah.
This I will find this very, very quickly. And the point is that we looked at the database. Just a moment, I will share my screen. At the database of flux ropes. Here we are. This is the database of flux ropes, and this is the center. The 0 hour is the center of flux ropes, okay? And about thousands of flux ropes observed out of ICMEs and CIRs. So this is the case of relatively quiet solar wind. And we have an amplification increase in energetic ion flux and in many energy channels. So it looks like this. Yes, sometimes we don't see anything, but statistically, these structures like plasmoids, flux ropes, they can be considered as sources of energetic particles, locally accelerated, obviously. We can debate the way of acceleration, the methods, the mechanisms, but this is something we published actually. Thank you very much. This is Leroux et al. 2020. Obj paper. Oh, not obj, maybe. Okay, you will find. Thank you. The next speaker is Xiaozhou Zhao. I could see him. Okay. Hello.
Okay, I'm going to talk about magnetic island emergence.
Just a moment. We cannot hear you properly. Can you increase the volume? We can do this in Zoom directly.
Okay. So can you hear my voice?
Okay, I can increase my volume. What about the others? I'm satisfied.
It's okay.
It's okay. Okay. Excuse me. I apologize for the interruption.
Okay. So I'm going to start. Yeah. So I'm going to talk about magnetic island emergence. It is a two-dimensional MHD simulation. Then we put test particles into the system and to see how the particles are energized around the O point. And this work is collaborated with Professor Ronnie Kappens and Dr. Fabio Buccini. It is supported by ERC Prominent. Okay, so this is the outline of my talk. First, I'm going to talk about the background of the research. Then I'm going to describe the MHD simulation results. Next is the test particle simulation results. Finally, is the conclusion. We know particle acceleration is an important process in solar flares. So it's important to get to know how the particles are accelerated. In solar flares, particles are believed to be accelerated during the reconnection process. So reconnection is very important. Previously, people approximate solar corona as MHD. This is reasonable because all the typical length scale in the solar corona is larger than the micro scales, like the bilength, mean free path, Larmor radius. So MHD approximation is a good approximation to the solar corona. So reconnection process can be modeled by MHD in solar corona. And firstly, people proposed the three-part reconnection model. It is a slow reconnection model. The problem is how to increase the reconnection rate to explain the solar flare timescale. Then people proposed the path check reconnection model. It's a fast reconnection model, but it's not self-consistent in MHD regime because in the central region, anomalous resistivity is required to make it run in MHD regime. The problem is how to trigger fast reconnection. Then people think about carrying mode instability. And the question is, what is the criterion for fast reconnection? What is the criterion for plasmoid instabilities? This is a topic still under debate today. So we are going to conduct MHD simulations to firstly to look at a magnetic reconnection process, then place the test particles into the reconnection current sheet. So firstly, we are going to simulate a reconnection process. We are going to solve this set of MHD equations. It is resistive MHD equations. We can see the equation 3 is the equation of energy conservation. It is, we only solve this equation without other physical effects like resistivity, radiative cooling, thermal conduction. All these physical effects are neglected. We only take into account the resistivity. The resistivity is said to be a uniform and constant value in the whole region. The initial condition is like this. It is a 4-island setup. The initial magnetic configuration is plotted in this figure. We can see initially it is a 4-island. There are black arrows overlaid on the picture. The black arrows is the initial velocity field. We can see this island and this island will be pushed towards the center, and this island will be pushed by the black arrows. Black arrows are velocity field. They will be collided with each other, and the current sheet will be formed here. This is the global evolution. The 4-island is the initial condition. This island and this island collide with each other, and a current sheet is formed. And this is the detailed structure of the current sheet. We conduct 7 cases with different global Lundquist numbers ranging from 10 to the 3rd power to 10 to the 6th power. This is a table listing all the numerical experiments we conducted. We find the minimum Lundquist number to trigger plasmoid instabilities, the current sheet, is well consistent with previous research. Is about 10 to the 4th power. However, we also found that the minimum Lundquist number increases as the resistivity decreases. But the minimum one is the same, but sometimes a higher Lundquist number is required. In order to confirm our results, we conduct a convergence test. The purpose of a convergence test is to show that the resistivity we set is reasonable, it's larger than numerical resistivity. To do so, we conducted 3 cases with the same resistivity values, but different resolutions. So the first case, we use 9 AMR levels. The second case, 11 AMR levels. The third case, 13 AMR levels. All the 3 cases have the same resistivity but different resolutions to see whether the results are the same or not. So the top panel shows the first case with 9 levels. The middle panel is corresponds to 11 levels, and the bottom panel corresponds to 13 levels. You can see here is a box. This is a close-up view of this box. And we select another box here, and the zoomed view of this small box is plotted in the right. So we can see we compare the results of the 3 cases. Let's look at the right panels, 9 levels, 11 levels, and 13 levels. All the 3 cases are qualitatively the same. We didn't find secondary islands as the resolution increases. So our results are believable it's reasonable to take 9 AMR levels to test the particle simulation, because even if we increase the level of resolution, we didn't find new physics. This is a comparison between different resistivities. This picture shows the results of the same resistivity by different resolutions. This picture shows the same resolution by different resistivities. The top panels shows the result of the resistivity 10 to the -4. Bottom panels 10 to the -6. We can see when resistivity is taken to be 10 to the -4, no magnetic currents are formed in the current sheet. But if we decrease the resistivity, Lundquist number increases, magnetic currents will be formed in the current sheet. We can see the video like this. We can see the top panels shows the result of the resistivity 10 to the -4, bottom panels 10 to the -6. The background color represents the mass density. Color red represents higher density, and color blue represents lower density. You can see the results. So these two islands collide with each other, and current sheet is formed here. In the top panels, we didn't see magnetic islands, but in the bottom panels, we see magnetic islands. We'll take this snapshot as the imaged background and put test particles into it. So this is the test particle simulation results we are going to show. The initial condition for the test particle simulation is selected as this island. This island is plotted here. Then we place the 5 particles into the system. The full trajectories of the particles are calculated. We didn't use guiding center approximations. The trajectories are fully resolved. The particle 1, 2, 4, or 1, 2, 3, 4 are energized. Particle 5 didn't energize because the simulation stops before particle 5 starts to be energized. The particle motion is governed by the relativistic equation of motion in the electromagnetic field. And here we use letter U to represent the fluid bulk velocity and letter V to represent the particle velocity. This is a 2D simulation, so we don't, the electric field is along the direction perpendicular to the simulation plane. In this simulation, the Lundquist number is large, so we can the electric field is represented by a resistive term and a convective term. We can compare the ratio of the two terms. The ratio of the two terms is equal to the magnetic Reynolds number. It's much larger than 1. So the convective term and this term is dominated by this term, resistive term. It can be neglected. Actually, doesn't influence the particle simulation results. This is the energy of the 5 protons. Proton 1 to 4 are energized. Proton 5, this is the energy curve of the proton 5, doesn't increase because the simulation stops before particle 5 starts to be accelerated, but particle 1 to 4 are energized. Then we are going to see what really happened in particle 1 to 4, why they are accelerated. In order to do so, we study the trajectory of particle 2 in details. The trajectory of particle 2 can be divided into 3 phases. The first phase is the guiding center drift. The particle 2 starts to move from the white point here and move by guiding center drift. It moves to the black dot here. This is the first phase. The first phase corresponds to the region shaded by color green in this plot. This plot is the energy curve. We can see in the first phase, particle is not accelerated. Energy is almost conserved during the phase of guiding center drift. After particle 2 reaches here, then phase 2 starts. Phase 2 is represented by color yellow in these two plots. The top plot is the energy curve. The bottom plot is the gyro radius. We can see the trajectory of particle in phase 2 is plotted in the right panel as red curves. This is a process of adiabatic motion. There is some adiabatic invariant associated with this process. After the particle is trapped in this small island in this white box, phase 3 starts. In phase 3, the energy increases a lot. We can see phase 3, the energy curve is plotted here. If we zoom this energy curve, it is like this. If we take a small time segment and zoom in, it is like this. It's oscillating, but the energy increases. We're going to see why the energy is oscillating and increases in phase 3. In order to do so, we plot the trajectory of the particle to check what really happened. When particle is trapped in this island, its trajectory is like this. We plot a cycle of motion. It is trapped in this island and it does bouncing motion like this. It moves back and forth for many times. During the process, the gyro radius is much larger than the size of this island. We can see the size of this island is about 50 kilometers. However, the gyro radius is more than 100 kilometers. So this process is a non-adiabatic process. It's non-adiabatic motion. We fully resolved the trajectory of the particle and found in the scale below the gyro radius, the particle does non-adiabatic motion and the energy can be accelerated. Why the particle can be accelerated in a scale smaller than gyro radius, because if we plot the electric field acting on the particle, we found the peaks of the electric field acting on the particle is a little bit larger than the values of electric field acting on the particle. So when the particle moves back and forth for many times, during each cycle of motion, the particle gains a bit energy from the electric field. We can see that this is a solid curve, and this is a solid curve represents the same value, same absolute value, but we can see the peak value is a little bit larger than the value of the valley. So when particle moves back and forth for each time, the particle gains a bit energy from the electric field. This is a Fermi process. We also did analytical analysis for this. Analytical investigation shows the particle gains energy during each cycle of motion is proportional to the ratio between the fluid velocity to the light speed. And this confirmed that it is a first order Fermi process. The first order Fermi process, the first order means its energy gained during each cycle of motion is proportional to the ratio between the fluid velocity to the light speed. And we have a video to show the trajectory of the particle. So the white dot is the particle. This is electric field acting on the particle. This is electric power. This is the proton energy. We can see the particle moves back and forth, and the energy increases. Electric field is plotted here because during each cycle of motion, the particle gains a bit energy from the electric field because the peak values of electric field is a little bit larger than the value of the electric field. This is due to the non-symmetric distribution of the magnetic field and the fluid velocity field. this can be proved by analytical study. Due to the limited time, I'm not going to show the analytical study of this, of the trajectory of particle 2, but this trajectory can be fully solved by analytical method. So we need to consider deceleration mechanisms. Otherwise, the particle energy will extremely high. This should be done in the future, but we mentioned particle collision and radiation reaction is two main energy loss mechanism during particle acceleration process. However, in this study, we didn't take into account these two these two energy loss processes. So the model should be improved to add deceleration mechanisms. In our simulation, we found the particles can be energized to hundreds of GeVs within tens of seconds. And this energy is actually extremely large, so deceleration mechanisms actually required. Our conclusion is a null point is a potential particle accelerator. The motion of a proton in our simulation is divided into three phases. The proton energy is mainly gained in the third phase. The third phase is a relativistic non-adiabatic motion around the vicinity of the O point. Also, we also found by analytical study, which isn't shown in this talk, that the energy gained during each cycle of motion, the bouncing motion, is proportional to the light speed. This is a result of first order Fermi acceleration. Okay, thank you.
Very interesting, thank you. Good job. Questions, please. Valentina, you raised your hand, or it was?
I just like the talk because it confirms. We published paper with my postdoc Shah and Jarkova 2018. We agree with you completely that magnetic island can be very good accelerator, especially squashed island. I was mentioned today in my talk, and but maybe if you look at the paper, we exactly found this Fermi type 1 acceleration of X null points neighboring the O null point. So this is a very good one. So I'm glad you came to similar conclusion from different point of view, but estimations. But we found this also using test particle approach. It works very well. And we managed to accelerate up to 1 MeV electrons within under 1 second. So it accelerates very quickly.
Yes, but you consider different boundary conditions and different sizes of this system. So it's, of course, the energy depends on the size of the system. And, excuse me, Xiaozhou, you considered this in a dimensionless box, or what?
Okay, actually, the simulation box has physical units. It has physical units. It's about tens of kilometers in this region.
Yeah, but it's quite big. That's why Valentina considered, I think.
Yes, in numerical simulation,
different.
All these equations are dimensionless, but you can add physical units when discussing the results. You can see the size of this island is about 50 kilometers, 5.
It depends on gyro radius of protons.
Yes, of
we measured
course.
gyro radius of protons. So maybe it will be 15 kilometers in heliosphere. It will be 0.5 gyro radius of proton.
Yes, that's what my question, because if you recalculate everything to gyro radius, probably the acceleration rate will be the same. And about the analytical solutions, I highly recommend you to read these papers written by Gary Zenk and Cobus Leroux. One of these, this is not the biggest one, But actually, they solved this kinetic equation. Laxman can tell us more. He's a theoretician, not me. Laxman, can you tell more about these results, about the analytical solutions?
Yes, yeah. So when they derived that analytical solution, they have considered that the length scale of island is smaller than the large plasma scale because particle needs to guide it. So, and they have used the gyro average. They derive doing by gyro average type of phenomena. And yeah, particularly they have assumed that that length scale that the gyro radius should be smaller than the plant that structure.
I'm talking about the mechanism, that practically several mechanisms are at work, and the Fermi acceleration is obvious, right? So,
yeah. They have particularly introduced like kind of a 3 types of mechanism. Like as I said, like there can be induced electric field that can energize, and also the islands can merge or contract. So they have included this kind of particle acceleration mechanism to derive the equation.
yeah, I will share the links to the last papers maybe here. So yeah, more questions. Okay, we are done with questions. Then Mitsuo, you are the next speaker.
Okay.
Yes, thank you.
Okay.
Can you see my screen?
Yes.
Okay. So hello, I am Mitsuo Oka at UC Berkeley. Today, I would like to report an event in which we saw unusual enhancement of 30 MeV proton flux in an ICME sheath region. So this study started a few years ago in Japan when we had a very small workshop on SCPs. And many of the participants were not so familiar with SCPs. So we started from the basics, such as the impulsive and gradual SCPs, and also how the time profile varies depending on the location, etc. And then we moved on to examine historical plots of Gauss and stereo proton flux. These are some examples. We browsed through these plots from 2000 up to 2018. And then we started to notice that there were some unusual events that look like this. Very spiky, short duration enhancements in the Gauss proton flux. So you can see these spikes. These events are not so often, but we found about 10 events of these spike events so far. And we confirmed that there's no clear association with flares, and also no clear enhancement of heavy ions. So these are not impulsive SCPs. And it turned out that almost all of these events are associated with interplanetary shock. So these are probably ESPs, I think. However, there was one exception, which is this one. This one also had a shock nearby, but it was not so clearly associated with the shock. This spike was not so associated with the shock. So we would like to report that we found this event today. So this is a background information of this event. So this is basically the high energy proton flux profile over 1, 2, 3, 4 days in the heliosphere. So here we have stereo A, stereo B, and also 1 AU measurement here. Actually, this event was also studied by David Lario in 2013, but from different perspective. I think he was focused on electron acceleration on the other side of the sun. But anyway, there was two SCPs on this during this time period, and we can see the corresponding time profiles here, the first one, and also the second one here. And the first one happened right at here on the June 4th, and you can see the chronograph image. And the second one happened June 5th here, and you can also see the chronograph picture here. Now, we can this second CME happens to be coincident with this spike event, but as you know, it takes time for the protons to come toward 1AU, and it's difficult to explain this spike event only from this second CME. So we then moved on to look at more details of this spike period, and this is the overview of the measurements by these spacecraft. There were actually multiple spacecraft at 1AU. So the top 4 panels here shows the GOES proton events, the GOES data from 2.5 MeV up to 30 MeV. And you can see the spike profile here. And also at L1 point, we have data from SOHO, WIND, and I'm not showing the data, but we also have data from ACE and Artemis as well. And in this 5th panel from the top, this is the spike profile measured at SOHO. And the 6th panel here is the profile measured at WIND. And WIND also had the plasma measurements as shown here. So you can see the typical structure of fast mode shock, sheath region, and then ICME. And you can clearly see there was a magnetic cavity here. And this is clearly associated with the flux enhancement at the SOHO and WIND. The GOES spacecraft detected the similar spike 1 hour later, which corresponds to the solar wind convection from L1 to 1AU. And because we had multiple spacecraft, we were able to do the timing analysis, and we found out that this structure, this cavity structure, was moving toward this direction as shown in the arrow. So it's a little bit tilted. And we had almost a similar result for the shock structure and also this interface structure as well. And actually, there was like 3 days before this event, there was actually another CME event that happened like this. It was on the other side compared to the 2 CMEs that I mentioned before. This one, the CME went to the left-hand side as shown in this illustration. So if you think about the structure of this CME or CME structure, probably Earth went through this structure on the flank side of this structure. So if we think about this geometry, this orientation derived from the timing method is very consistent. Anyway, we further zoomed into this magnetic cavity. And as you can see, there was lots of fine scale, small scale structures in the cavity. So it's very turbulent. So here's the spectrum in the magnetic cavity. So left-hand side panel shows the frequency spectrum. So horizontal axis shows the frequency and the vertical axis shows the power spectral density obtained by the wind magnetic field data. So inside the cavity, the turbulence level was enhanced, although the parallel index remained similar outside the cavity. The right-hand side panel shows the particle energy spectrum. The horizontal axis shows the energy from 1 MeV to 100 MeV. The vertical axis shows the particle flux. And as you can see, above 10 MeV, the flux enhanced significantly, and also the parallel became more flat, as shown here, inside the cavity. Below 10 MeV, the parallel spectrum stayed the same, remained the same inside the cavity. By looking at the details of the turbulence, we found so-called magnetic holes, which are very small scale structure, magnetic structure. And in the past, people have discussed that these kind of magnetic holes are remnant of mirror mode instability. By the way, in these magnetic holes, the magnitude goes down, but the direction of the magnetic fields doesn't change very much. And anyway, recent 3D PIC simulation shows that they are rather produced out of decaying turbulence, not necessarily the mirror mode instability. So detection of these small-scale magnetic holes may indicate that turbulence level may have been even higher in the magnetic cavity before the spacecraft detected this cavity. So anyway, what I wanted to say here is that this magnetic cavity had full of strong turbulence. I know people often talk about preconditioning of particle acceleration, and in this specific event, the spike was here, and 4 hours before the spike, there was a shock here, and you can see, if we look at the lower energy particles from 0.1 MeV to 1 MeV, you can see particles already were accelerated at the shock front. So this could be the could be a preconditioning or pre-energization before the main energization in the cavity. But there was also another SEP-like profile in the ACE data. So this may also be the preconditioning. Anyway, here's the discussion and conclusion. We found this spiky enhancement of 30 MeV protons clearly associated with the magnetic cavity in ICME sheath region. And the turbulence was intense. The energy spectrum exhibited hard parallel. And also this event may be one of the atypical energetic particle event that these authors has been discussing. And they usually use magnetic reconnection to explain the particle acceleration. In our event, I think this event is very similar in a sense that heliospheric scale structure was involved. There were the total of 3 CMEs involved. However, this event is unique in that energy reached up to 30 MeV, and the flux enhancement was clearly associated with the magnetic cavity with enhanced turbulence. We still don't know the precise mechanism of proton acceleration in the cavity, but anyway, we thought this is an interesting event to report. And that's it. Thank you.
Thank you. This is a very interesting event indeed. And this is again about this specific turbulence, which sometimes occurs within ICME sheaths. I have a question, may I?
Yes.
Oh, yeah. What about the ICME itself? What was the history? Maybe it was the case when 2 ICMEs merged, and so the sheath was so enhanced. What do you know about the history of this guy? Yeah.
Right. So in the in situ data, we don't actually see the evidence of these 2 CMEs, except although we see the SEP enhancement associated with these 2 shocks. So I'm not really sure how these 2 CMEs interacted with the spike event we saw here associated with this green structure.
Have you tried to look at the IPS interplanetary installation data?
No.
Because yes, it's interesting. You reported an excellent event to be studied in the future, because what you see here, you know, sometimes we cannot predict how different streams and flows interact and what we get at 1U. That's the biggest problem of weather. So maybe something like a combined event. Okay, excuse me. Other questions, comments? Interesting event, really. Oh, okay. Nobody. Well, then Harald, please. Thank you again, Mitsuo.
Thank you.
All right, I'm gonna share my screen now when I can find it. There we go. Okay, I guess you can see it.
Yes.
All right.
Not like a full.
Oh, I'm sorry. I go on full screen right now.
Yeah,
Okay.
perfect. Thank you.
All right, this is the continuation of yesterday morning. I'm talking about energy dissipation of filamentary structures downstream of the Earth's parallel bow shock. And this is just to, you see my cursor, this is to acknowledge my co-authors. They are in different parts of the country. So in Boulder, Steve Schwartz and Caroline Strutton at UNH, it's myself and Charles Farrugia and Imogen in the UK. This leads me to my outline. So I want to motivate why we are going to do this. I think this is just preaching to the choir why we are doing this, because all the people know exactly. We have had many discussions today why current sheets are important, why the filamentary structures are important, how they contribute to the thermalization or energy energy conversion of kinetic energy into thermal energy and vice versa. So what we started is we looked into bow shock crossings. We had a couple of many events actually. We made a catalog of shock crossings associated with current sheets with MMS. And I just going to talk about one on the 31st of December in 2019 with all the spacecraft instruments. But we have a whole slew of catalogs and shock crossings associated with energetic particles and current sheets. We didn't make that public yet. We have it in a group. If somebody wants to see it, very welcome, just contact me. Then after I discuss in detail the shock crossing on the 31st, I'm going to go into the discussion of the observational results before I actually go ahead and summarize everything together. So motivation, I pointed out yesterday, there were many people before, and looking at bow shock crossings and energetic particles, and what in 2007 in one of the Nature paper, Alessandro Retino found is these kind of currents, these kind of spectra. Here's the shock crossing, here's the energy spectrum. And you can see there's a little bit, there are spikes in density and magnetic field, and also spikes in the spectrum of energetic particles. They said, well, it's most likely we have islands, and the configuration of these islands, they can reconnect, and then reconnection is one of the accelerators of these ions. The question, of course, is it really, is it enough? So they came up with small-scale reconnection. Later on in 2019, Imogen looked also into simulation and observation, and she also focused close to the bow shock, to the ramp area, to the shock transitional region, not too far downstream, but at the transitional region. I mean, there was a reason for that, because when you want to have strong currents and you want to have really turbulence going on, where you find the turbulence, of course, is the strongest in the shock ramp region. They also pointed out that these might be, small-scale reconnection events. What they found, though, that the acceleration was not that great, the thermalization was not that great. They concluded at some point in time, oh, well, this is all just to relax the magnetic field in the shock ramp. So, yeah, maybe not. What we did now, we generated a catalog with MMS data from 2015 to 2020. There are many bow shock crossings. And the events we looked at were periods of MMS burst data, so really high resolution data. And we looked at magnetic field activity bigger than 20 nanotesla. Indication of current sheets, of course, you need to look into the currents before, and you have to make a couple of assumptions how you identify a current sheet. And we focused on periods of energetic particles. One of the events we picked out is shown here. The orbit is shown here on the left-hand side. On the right-hand side, this is browse data, what you're going to get. So This is the magnetic field data. This is the energy spectra. This is the electrons and the omni data in the electrons, and this is the density. So what you see here? Here we have an inbound crossing. We have a little snippets of the bow shock crossing. Then we go upstream again, and then the bow shock occurs. And when you look at this here, it really looks like a perfect bow shock crossing, because you have accelerated ion right at the crossing, and then there is nothing to write home about later on. But on the outbound crossing, on the other side here, what you see is a lot of the spiky events in the energy spectra, and as well as in the electrons, also in the ions. And you find, yeah, it's a little more turbulent on this side. So my first idea was, well, yeah, okay, maybe there was some event going on that made this thing here more quiet than this side. But I said, well, let's focus on what's going on this side here, and this is what I actually did. So the density, I must say, the density of the ions is pretty much constant. It's not really something to write home about, where people can say, well, yeah, of course, we have the upstream current sheets. They are going into the shock ramp. They are convected downstream, and that's what you see. Well, not really. So we focus on this side here, and this is now what we have is FBI data, so the fast plasma instrument for the ions. And all what I'm doing is, so here we have these bow shock crossings on the lower panels. Here you have the bow shock crossings. I really go far downstream. I am not focusing on the shock ramp region, because I said, well, what's going to happen actually with these spikiness down here? And you can see it even a little bit lower in energy. So the magnetic field of this time frame here, I pointed out from here to here, is blown up here. We go up in the resolution. And yeah, of course, then you lose the resolution up in here in the energy spectra. But what you can see is a change, a sudden change in turbulence. So this is the total magnetic field. And down here, we have the components of the magnetic field at the spacecraft at MMS. And so are there current sheets? Well, the point is now, if you focus down here, let's see. Yeah. And what we did is we looked into the spectra. We really looked into not the distribution function, I'm sorry. So we looked right here where it's relatively quiet, and then we looked down here. So what we found is, first, we see a relative quiet spectrum here, which is right here before the turbulence really starts. And we see, well, this is a typical downstream distribution. It's a little more, a little more heated, but it's not like the upstream distribution, which would be peak light. So there is a little bit of stuff going on. But if you look just a few seconds later, you see really that in the distributions, you get flanks. You get tails in the distribution in the incoming flux. So all of a sudden, what you see is you go from a relative quiet downstream distribution to a distribution that indicates that there is generation of tails in the distribution. And generation of tails, really, I would attribute it to turbulence, small scale turbulence, which we actually find here. And it's not so small scale, it's actually, it's actually pretty hefty. But it happens pretty fast in matter of you see it here in matter of seconds. So it's 23, 21, 23, and then later on it's 50. So it's about 30 seconds from here to here. All right, are there current sheets? Well, yes, there are current sheets, and they're isolated and intense. And the this is another study we did. We identified all the current sheets, in, not just 1, 2, or 3. We identified more current sheets. It was at the order of about 100. And these were thin current sheets, and I studied this with Stephen Schwartz. And what we found is when we distributed these current sheets uniformly in the downstream region of a normal shock crossing, we found that the downstream, these current sheets actually dissipate energy up to 10%. So they convert a significant fraction of the incident energy of the shock that actually arrives at the shock, up to 10%. So it's not the lion's share, it's about 10%. You can say, well, is 10% significant? I would say yes. And it was a uniformly distributed. And so people can argue, you can say, well, but it's not so much in closer to the shock ramp. But then I would argue that closer to the shock ramp, people haven't seen a lot. So you would see even more when you go further downstream, where you find more current sheets. One thing, though, I want to really point out, and we have heard it today, we have the current sheets in the solar wind. So they are certainly convected to the bow shock, and they are certainly convected downstream to the bow shock. So we have these current sheets, but the shock itself creates turbulence. It creates turbulence, and in addition to the many current sheets that come from the solar wind, you probably create current sheets downstream just because they are generated at the shock ramp and convected downstream. So this might also be a contributor. And the question is now, does this provide energy dissipation? The answer is yes. Does it provide energy acceleration? Most likely, we need to go a little bit in more detail, but what I really want to point out here, so this is even getting further downstream. So another tiny little sliver here, we blow up. And we look at the electric fields of the double probes and also in the magnetic field. And then we calculated the currents by curl B. So J is calculated, the current is calculated by curl of B. And what we find is, yes, there are current sheets here. There are current sheets here. And but what we also find is, and this is really significant, we find a lot of spikes in the electric field. Currents are not current spikes, but strong. Let's say if you find a spike, you find a good gradient. So there are gradients in the electric field, and we know when we have gradients in the electric field, you can accelerate ions. So in terms of the energy transfer, what we did is, first of all, we used the electric field and we transferred the electric field into the downstream rest frame. People can say, of course, you have a moving downstream rest frame. So what are you talking about? There is energy and you can get energy out of it. But we put it in the downstream rest frame. So the EJ, or the E, the E with the hyphen on it, is the electric field in the downstream rest frame. This is in the electric field, excuse me, electric field in the spacecraft frame. That's in the downstream rest frame. It looks different. Sorry, it looks different because of the shift or the transfer in the downstream rest frame. So for the energy transfer, we took the J of curl B. We took J dot E, you get the energy transfer. If J dot E is positive, that means you take energy out of the field. If J dot E is negative, you put energy into the field. So particle would lose energy. If J dot E is positive, particle take out energy of the field. So that's the way we transfer. In essence, you can see there are a couple of spikes where it's indeed positive. There are a couple of spikes where it's indeed negative. So you have a balance between, it's a sort of giving and taking. So particles will gain energy, particles will lose energy in the turbulence. Yeah, that's normal. But if you integrate everything up, you end up with a positive J dot E. So the transfer from the field to the energy is positive on average. And in the downstream region, so particles gain energy or they transfer energy. So there is clear indication for that. So what does it mean when you look at this plot? And it's more or less my summary plot. So you have locations or times where you have a strong electric field and you have strong currents. You have times where the J dot E is positive, J dot E prime is positive, though particles take out energy of the field. And so this happens all far downstream. It's not like it's really in the, you know, what you would expect with the diffusive shock accelerations right at the shock front. No, this happens really far downstream. So it is indeed, these current sheets are a contributor to the downstream thermalization. What the electric field is doing and what the spikes and the turbulence of the magnetic field is doing. We know that we cannot accelerate particles with the magnetic field, but we can scale up those particles. We know that we can accelerate ions in the electric field or gradients of the electric field. So maybe you find gyrocenters where you get energy out of the electric field. But on the other hand, there is an interplay. So what we are actually doing right now, before it go to the summary, so I've written a program where we can scan the downstream region for current sheets. So the J dot E in the current sheets for the electric field, we're gonna pick out and make a statistical study. How often those gradients in the electric field, how frequent they are in the parallel and perpendicular region, and how frequent the J dot E is positive in the perpendicular or parallel region. And then, of course, what we do with the simulations, where you can really study particle trajectories, but not, let's say, in observation. You cannot study particles in observation. You really figure out what's going on. That's where we are right now. So to summarize, we made a list of shock transversals with using MMS data, and we looked at the downstream region. We have examples, and we have more examples than just that one, but I don't have too much time, where you're using FGM, FBI, HPCI, EDP data to look and analyze that in more detail, or in the detail we can. We used the burst data because those are the high frequency or the high cadence data. We found strong evidence that strong turbulence is associated with the energetic particle distributions far downstream of the shock. And this is also with the isolated current sheets we find there. So we have isolated currents as we have strong electric fields, strong gradients, and for sure they are a contributor to the relaxing of the magnetic field, but also to the thermalization and the conversion of kinetic energy into the thermal energy. And I think I'm gonna stop there.
Thank you. That was brilliant.
Thank you.
Questions? We had so many questions during the official sessions. People are satisfied, actually.
Don't be shy. Don't be shy.
Okay, so I have one question.
Go ahead.
Okay, so yeah, as you mentioned, a current sheet in the downstream region. So I was wondering, like, at what distance from the shock position you can see that kind of current sheet? Because in some cases, from the this particle acceleration, also like the particle sometimes particles sometimes do not like accelerate just after this shock position, and it energizes after a certain distance. And it can also be shown one of the simulation by Masaru from hybrid simulation that after a certain distance from the shock position, and he found like a lot of island there. So I was wondering.
Yeah, so I probably show you this figure here, how far downstream we are. I would say we are around here. So it's pretty far downstream. And I can look in detail how many RE we are downstream of the shock, but we are not even close to the shock ramp region. That's what I can definitely tell you. I had the same question as you were asking, and I really wonder how far we can go downstream. But without having done this statistical study, I only can tell you a handful of occasions or locations where we have really found these currents deep far downstream. But I cannot give you an average number, let's say over 5 years or so.
Okay, thank you. And what is the mechanism for you to find a current sheet here?
The mechanism to find a current sheet, what we do is we look into the magnetic field where you see a traversal of, let's say, maybe I can show it to you. So we look into the magnetic, probably not. Maybe I use this one, it's okay. So we look into the magnetic field. So that's one component. One component should be steady, the other one should switch the polarity. We look for those events, and of course we have this all the time. What we do is we look into the high resolution magnetic field data and we look on the average, and then we take 3 standard deviations to get a response for that. We also look into the density, and we also look into, we calculate then the currents, and then we look into the currents, how high the currents are. So we use curl B, the rotation of B, to get the currents out, and then we look how high the current is.
Okay, thank you.
We have a threshold there. It's a lengthy process.
Okay, thank you.
Harald, I have a question.
Sure.
In a recent simulation by Klein et al., they have shown that there is an anti-correlation between G dot E and heat flux. And the idea is that if particles gain energy by wave-particle interactions, then the heat flux can take the energy away from the volume. So maybe it would be reasonable to consider heat flux if it could be calculated from MMS data.
Yeah, that's a good point. My first thing was that we have to really go downstream in the downstream rest frame to get a really good answer of the J dot E. That's why I not use the E of the spacecraft in the spacecraft frame, but in the downstream rest frame. Yes, I'm aware of the heat flux. Not so easy with the data, but I will try. It's certainly possible, but I haven't done it yet.
Thank you.
Sure, you're welcome.
Thank you. Other questions? All right. Thank you. It was very interesting. Thank you, Harold.
So then I stop sharing. Okay.
Yes. Rui.
And if there are some other questions which may come up later, shoot me an email. You're very welcome.
The topic is very interesting because actually we have a lot of, we can see a lot of similarities between this downstream region and, for example, ICME sheets and even the termination shock, heliospheric termination shock. It's all about intuitively, we understand that it's all about the same, but yes, details are different.
So, yeah, it's like, you know, these are small, you know, we had a lot of discussion, I can tell you. People said to me, what do you want to do with all these small scale stuff? It doesn't really contribute to it. I said, well, yeah, look at ants. They are small, there are many, but they can move a mountain if they want to.
Good. Okay.
All right, folks. Thank you very much.
Thank you. Rui.
Hello, Olga.
For your talk.
Yeah, I am. Sorry. So just one thing, the session is being recorded, right? I didn't have the possibility of following all of it, but there were plenty of very interesting talks here and there that I would like to see again, if possible. All right?
Yes, sure. I have recording. Actually, I have to, I will share this, excuse me. Was this a question?
No, that was my son. The question for me. Yeah, the question for me, not for you.
Okay. Well, I will share these things on YouTube, and now we are sharing this session live on YouTube.
All right. Okay. So let me just share my screen, and while I do it, well, I want to thank Olga for having warned me about this session and make me participate. That was very nice. So I'm going to talk about is a bit different than the previous talks in the sense that I'll be looking at the sun, or actually the solar corona, and rather at large scales and forcing of rotation and rotational shear at large scales. So this came up this is described on a paper that has been recently accepted on ANA about 2 weeks ago, and I'll share the link to the archive preprint if you want a bit later on. So the motivation for this was, it came from different regions. I have a long-term interest on understanding how the rotation in the corona and on the solar wind settles as a response to whatever is happening at the surface, differential rotation and so on, at different phases of the cycle, and all of these. But there's also that recent results, or the first batch of results by Parker Solar Probe, have shown a series of different phenomena that either phenomena related to turbulence and to switchbacks and all of these, sometimes to the formation of flux ropes and these kind of features. And at the same time, you could see that there are sometimes very high transverse velocities, and not just high, but there's a certain level of variability within the regions that were probed by Parker Solar Probe, right? So there's that. A bit more recently, though, not recently, but more pragmatically speaking, within the Solar Orbiter Consortium, oops, sorry about that. We have been dealing with the problem of figuring out methods to do, well, as automatically as possible, sun to spacecraft, so Solar Orbiter or any other spacecraft connectivity. That means magnetic connectivity, but also connectivity in terms of the solar wind propagation and so on. So this is done with typical tools, magnetograms, extrapolations, and then spirals, for which we provide a solar wind solution, a solar wind acceleration profile, which is one of the source of uncertainty when you're trying to pointing out whatever, or to connect phenomena at the sun with phenomena that is measured in situ at the spacecraft. But rotation itself alone is an unknown, and that plays a role in that. So there's those two sides of this question. There's the issue of understanding rotation and angular momentum transport, but there's a pragmatic outcome to that as well that we need to solve in a way. So what I'll be showing you is the first investigation of, well, from our side at least, of coronal rotation, that we try to justify, or at least to relate to observations that were done in the past by UVCS, in the old SOHO UVCS days, and for which we are also trying to make links with new instruments such as METIS on Solar Orbiter and WHISPER on Parker Solar Probe, as you'll see. But so, just to cut straight to the chase, let me take my away. Simulations I'm talking about look more or less like these. So I've run a series of MHD, global MHD simulations of the corona that span a whole solar cycle. So this is based on more or less idealized coronal field topologies that represent several phases of the cycle from solar min to solar max. Okay, so here I'm showing just a few snapshots of that. So the first column represents solar minimum, a typical solar minimum, the one at the middle solar maximum, and then the third one, a moment of the decay phase of the cycle going towards the following solar minimum. In all the panels, just let me take a little time explaining this. So each panel is divided in two parts. So the left side shows wind speed in terms of in units of Mach number, so supersonic wind in yellow and subsonic or no wind in blue. And the right part of the plots show you the rotation rate, so omega, right? Where bright means faster rotation and dark means weaker rotation, right? Now the difference between the top and bottom plots is that on these ones at the top, I've imposed a standard Snodgrass type differential rotation at the surface, while on the other one, I've imposed a solid body rotation just as a cross check. Okay. So on all lines, of course, the blue lines are magnetic field lines that open up as the wind pushes them outwards into the interplanetary medium. So what is there to be seen? There's a number of things that may eventually catch your eye from the beginning, which is that the closed field region streamers, but not only that, all sorts of closed field regions, will try as hard, well, will tend to set themselves into solid body rotation, or if you prefer, they will try to cancel out or equalize the shearing between their respective foot points on one side or the other. So if we are at a situation which is more or less equator symmetric, we'll have a stream rotating essentially in a solid body manner, although there can be some gradients inside the streamer itself and some global oscillations and so on. When you're on the open field, the wind will start forming what will become a spiral, well, a Parker spiral to make it simple. It can be a bit more complex than that, but it's a spiral. Right, so there's a number of smaller sub-features that appear. I won't talk about all that. I'll just call your attention to what's happening there. For example, at the boundaries, just at the outsides of the streamers, for example, these big equatorial streamers, these darker patches there, for example, but also these ones here, like that, or even there. Okay, so these dark patches mean lower omega, so slower rotation, while these ones mean slightly higher rotation. Just for info as well, so the surface, it's not really the surface of the sun, it's the bottom of the corona, is plotted with the same colors. It represents omega as on this side, just so that you have a visual reference on that. So that's, well, a bit qualitative. And so just to show you this a little bit better, I'll present on the next slide a series of cuts, of radial cuts taken at different heights that will show rotation period as a function of latitude at different heights for the same configurations. Okay, so there you go. So solar min on this side, solar max here, and decay phase on this side, differential rotation on top, and solid body rotation at the bottom. So the red curve on each one of the plots represents the imposed rotation profile at the surface, right? While the green curves represent cuts of the rotation period at 1.03, well, almost 1 solar radii, 2, 4, 8, and 16. Okay, so this is very low corona, and this is very high corona, well above the streamer heights, streamer altitudes. And so there's a number of, again, of structures that appear at different phases of the cycle. I won't speak about all of them because it would take a lot longer than I have. I'll just call your attention to these kind of features there that correspond to the darkenings on the omega plots that I showed before. So see, any of these curves, these ones, the ones that are pointed down here, you have this rotation rate that establishes at a certain height of the corona that tends to converge towards a more or less solid body rotation type. You have the streamer that is rotating usually a bit faster than the rest, so it's a lower rotation period. And then you have these bumps, like a double horn structure that really traces out this boundary between the two regions. So these things are robust and they appear all the time. They're very visible on solar min because of the large equatorial streamer configuration, but they appear on other phases of the cycle at different latitudes as well, such as, for example, those little bits there and there. So at first, I was very intrigued about all of these, and the first reaction as a modeler I had was that there should be something wrong about this and it should be the numerics, but I took a while to, well, be convinced that no, this is actually, these kind of gradients are forming against spurious numerical effects instead of the opposite. And then that led me to look at the literature. And this is more or less the kind of picture I found from the synoptic UVCS campaigns from a few years back. So this is the result here was published by Giordano and Mancuso done in 2008 by running a synoptic campaign that would place a number of slits, well, of UVCS slits over the plane of sky as is shown on this picture, and from that they would build a map of the at any given height there will be a map of UV emission as a function of position angle. So latitude is North Pole and this is North Pole again, so this is equator, South Pole, equator again, as a function of time for a number of time, for 1 year, for 1 month, or so on. They use two different types of lines, oxygen 6 and Lyman alpha, because they will give you some information at they will be more efficient at different latitudes, to be fair. So when you put this all together and average in time, so to say, you get this kind of distribution there, right? So you have the inside of the streamers here, and then the separation between streamers and the coronal holes there, and then the coronal holes with a decreasing period once again. So you have these slowing downs that are not exactly of the same amplitudes of the ones that I've showed you before, but they're of the same kind, and they should, in principle, be present at different heights all across the streamers. So this at solar min, which is a more or less, where you have a more or less clear configuration and can understand these things well. At solar max, things get a bit more complicated, right? Because there's more variability and so on, and the distinction between the two different kinds of lines becomes more complicated. To the point that when you start averaging out these kind of observations over long periods of time, you tend to find a rather flat rotation rate as a function of latitude, almost get you convinced that everything is in solid body rotation. But then if you decrease the periods of observation, of integration, if you prefer, to something like a month or even less than that, you start recovering once again these kind of variations that we tend to interpret as the kind of variations I've shown you before. All right. Anyway, so this is this is the kind of observation we can do of this kind. There were not many more available. We'll try to do this again, but this is what we have so far. So of course, when I'm from UV observations, when we speak of rotation periods, what we are measuring is recurrence periods, of course, that we interpret as plasma rotation periods. There's a caveat there, maybe, but that's the only assumption we are making here. So this is it. The interesting bit now for me is that, well, there's one important point, which is that rotation at the corona is complex with substructure. It doesn't look like the one that is right at the photosphere. It looks different, and it looks different in response to whatever is the magnetic field topology at that moment. That also means that there are gradients that are imposed in the corona, and that can be spatially extended eventually and long-lasting. All right, and so this is what I went on to investigating afterwards. So this series of panels there show you they show the amplitudes of the gradients of the wind velocity in the meridional plane, and then here at the top, and then at the bottom, the amplitude of the gradient of omega rotation rate, right? So these gradients here at the top are provoked by differences in solar wind speed from slow wind to fast wind, not just rotation, while these ones at the bottom are provoked only by gradients in rotation rate. So the typical situation is that at solar min, you do see that most of the shearing, either by the differences in solar wind speed or rotation rate, appear at these kind of interfaces, once again, which is really the interface between streamer and coronal hole. At solar min, at solar max, you have the same kind of behavior, but spread into a lower range of altitudes. And then you have different types of substructures as well. So you have one equatorial streamer there, for example, on this configuration there, which is of the same kind of that, but smaller. So that is with a heliospheric current sheet developing from hereafter. Then you have these kind of structures that are not like these ones, that are more like pseudo streamers, right? That develop some shears all above, but that have no large scale or primitive current sheet above them. What is the, yeah, so there's just one secondary point that is important to make, which is that these gradients tend to extend or to be measurable well above the heights, the maximum altitudes of the streamers I have anywhere in my domain. Okay, so I can see them up to at least 15 solar radii. So there's that. So this is gradients. Gradients mean. So gradients mean shearing, and as the shearing happens in 3 dimensions, that also means vorticity, right? So these plots here show exactly the same configurations, but I'm showing the amplitude of the vorticity that is perpendicular to this plane, or actually perpendicular to the magnetic field, while at the bottom, I'm showing the component of the vorticity that is field aligned. So to make a long story short, the non-field aligned or the orthogonal vorticity component will develop at the same places where the strongest wind velocity shears appear, which is there and there, while the structures like pseudo streamers, like this one, tend to form elongated columns with a vorticity that is mostly and predominantly field aligned, and that can extend to reasonably high distances above what I'm showing on these specific panels. So there's this. What else is there to be said? So shear vorticity, and of course that also means that velocity and magnetic field vectors will develop different pitch angles, which tend to be small at these altitudes because we are still close to the solar surface, but still visible. So I'm showing the same thing again, solar min, solar max. At the top, I'm showing you the ratio between the azimuthal velocity to meridional velocity, so the pitch angle of the velocity vector. I won't say too much about that. And at the bottom, we'll see the same thing, but for the magnetic pitch angle. Okay. The solar minimum situation remains reasonably classical, so to speak. The solar max becomes a bit different in the sense that some regions, specifically regions of weak field, can develop once in a while rather high pitch angles unexpectedly, and the pitch angle of the spirals that are above them grow faster than anywhere else also above there, right? Yeah, so this is it. So this is for the theoretical part of this work. And once we were looking at this, I started looking at, again, Parker's law data and so on, and trying to figure out whether the flows that we were measuring in situ, how they related geometrically to these kind of features. So for that, I took what we call the connectivity tool. That is something that we've developed within the ESA group, the modeling and analysis group for solar orbiter, which is essentially a tool that tells you almost instantaneously how we expect a spacecraft to be connected to the surface of the sun. Okay, so I won't tell you all the details. What I'm showing here is that there's a map of the emission where you can see the boundary between the kernel holes and the streamers, called field regions, the trajectory of PSP projected back to 2.5 solar radii, and its position there given by the star. So at each time we take the speed of the bulk wind speed measured at the spacecraft to build our solar wind solution down to the surface, and then connect that to, in this case, a PFSS solution. So those green points there show you the expected connectivity points at the surface, or actually solar wind source regions, and you'll see for each instant a series of them, not just one point. So what you get is a cloud of points that represent the uncertainty ellipse that we have for this estimation. I'm going to show that again. Okay. So as the spacecraft goes by, you have these points here and sometimes those points there. There's a lot to be said about that. The main point for me, the one that I want to raise here, is that for most of this specific Parker Solar Probe encounter, not just this one, at least the first 4, almost 5 encounters, the source regions of the solar wind measured by the probe were essentially scanning this long, elongated, and almost axisymmetric boundary of a large streamer and a bulk kernel hole. You could have connections from these to that side as well, but that side is of the same kind topologically as this one. Once in a while, we have connections to active regions or small kernel holes, but those are just occur once in a while. While the kind of transients we're trying to look at, switchbacks and flux probes and these kind of affairs, are occurring pretty much everywhere. But we'll get to that in a second. So just to represent exactly the same thing, but in an easier to see way, these two plots represent 3D renderings of one specific instant of the movie before, where there's this is the surface of the sun with a magnetic field on top of it, so red and green different polarities. This gray surface there is the boundary between the streamer and kernel holes. And all these lines there are magnetic field lines that are likely to be connected to Parker Solar Probe, with the red ones being the ones to which we attribute the highest likelihood. So the point there is that even when we attribute a large dispersion around the position of the spacecraft to uncertainties of different sorts, the expected source regions they all concentrate back down to these kind of regions, which are the regions I was telling you about, right? So the expected solar sources for the solar wind probe IPSP and also their acceleration regions all go across, right, this kind of positions around there. And so that's the point we try to make on this paper. Okay, so the consequences of that are still uncertain for us. So what we are trying, but at least I'm trying to hint at, is that these kind of shears, they are not necessarily always of very strong amplitude, but they are very persistent in time. They're always there because, well, they are forced by gravitational rotation, and they are spatially extended. And for that, we expect that though they could be a source of, we are looking at shear instabilities and these kind of things. Well, if they are not causing structures that we measure in situ, they should at least influence or impact the way they propagate outwards from the sun up to the spacecraft position, and that's something we still need to look at. So just to sum this up, what we find is that there's always a source of enhanced shear that is forced constantly at streamer or pseudo-streamer boundaries, and this is at all moments of the activity cycle, right? And this is independently, this happens even if the old magnetic field is perfectly symmetric. You don't need to have fast wind streams pushing slow wind streams and these kind of things. They at least, well, on large equatorial structures, at least rotation periods seem to peak at the outside of streamer boundaries, as observed by UVCS. Well, it's the only observations of this kind that we have, but they respect that. And more than that, one important consequence is that the rotation rate of the corona is very complex structured, and that there are many neighboring flows that have different rotation rates, high and low at the same time. So that could maybe explain a bit the kind of dispersion we have in VT, V transverse at Parker Solar Probe. And last but not least, these kind of structures, of shear structures that can be translated into vorticity structures eventually, can map out to large heliocentric distances. Large here mean a few tens of solar radii, right? So what are we trying to do? What will we try to do from now on? We are trying to plan campaigns using solo instruments, METIS in particular, to try to extend this the kind of synaptic campaigns I've shown. Also, we are also looking at WHISPER because we think we have seen waves that look a bit like Kelvin-Helmholtz waves being formed at specific regions of the aside streamer belt. The next steps are, of course, trying to connect this to in situ. We have studied an event for which we detected, we think we are convinced that we detected well-developed Kelvin-Helmholtz waves already in the heliosphere at the position of solar orbiter, that we think, but haven't demonstrated yet, that are connected to structures, more or less of this kind here, of this pseudo-streamer-ish structures like this. So we are speculating that those could have an impact, that kind of shearing structures could have an impact on the formation of these, these kind of instabilities. There's that, and of course, what's left to be done is to connect this to whatever is happening higher up in the heliosphere, and that's something clearly for remote work, well, to be done in the future. All right, so I think I'll stop here. I could have a few more slides to show, but that's not necessarily. I think we're getting a bit late already. And I'll let you ask any questions you may have about this.
Thank you, Rui. I say after every talk that it's very interesting, but it's really very interesting. And you know that I was happy to see these results because this straight out feedback from your study, from your theory practically, that you simulations, if we extend them to the solar wind, we get sources for current sheets, and this is very important. Okay, questions?
I have small questions. Do you cross the elephant surface in your modeling? Because you know that near the sun there is an elephant surface, and in some models there are some interesting effects near this surface.
such as these critical surfaces are in the domain. They have to be, otherwise the solar wind solutions I have wouldn't be sane. Let me see if I can. I didn't bring a plot for that. I should have. I'll try to just point them out. So sonic surface is less interesting, but that corresponds to that. The Alphen surface here, it goes as high as 10 solar radii and as low as 4 solar radii in this zone sometimes at equatorial regions. So they are well developed. They are fully contained within the domain at all moments. So these forcings are happening mostly in the subalvenic part, I think, for the most. There could be 1 or 2 bits that are not, but for the most they're happening under those surfaces. We don't see, I don't know if that's what you're hinting at, but we don't see the development of extra, we don't see the change in the type of turbulent structures across the critical surfaces, because this is still a global MHC model and so on. But I think I'll redo these by using a larger, more sophisticated model for that, actually. We'll see. But in any case, the effective forcing is happening low down in the corona, and then it leaves an imprint further up, but the forcing itself is happening low in the corona.
All right. I have more questions, but we will discuss this later as we agreed.
Yeah,
not today. I mean, we will find some time.
Oh yeah, for sure.
Next week maybe. Okay. Laxman,
Okay,
you wanted to ask some?
Yeah. So from your work, you have shown a shear. So I was wondering from at what distance from the coronal base the shear starts.
At what distance from the coronal? Well, I think this is the best way of showing that. It starts from the beginning. I mean, it starts almost at the surface. The maximum shear will be. Can you see my cursor? For example, on these big structures, the maximum of shear will be somewhere around here, but you'll see that here. Can I show this better? Well, I could have a plot or so. Oh yeah, this will do. So for example, don't bother looking at all the plots. Look at the one which is here, bottom right side. So this is a pole on view. So from the top of the, these are not field lines, these are flow lines. So I'm just tracing the flow. And it's flow that crosses this region. So the 3/4 to the top of the streamer boundary, so to speak. So these lines there, and this is on the inertial frame, so the sun is rotating from this point of view. So you have these lines there, which is a plasma that is rotating with the sun, almost solidly. And you have these lines there, which are the ones that are a bit far away already from the boundary, and then they behave just like normal solar wind. Then you have all these intermediate ones that show this bending and a transition between, kind of a transition, that's a bit extreme to say, between these two regimes, and this is the zone where where the strongest shearing is taking place, right? So if you want to map that back onto a side view, that happens there. And on these plots here, that's happening around here, okay? Here, there as well.
Yeah, but below the sonic surface, the solar wind speed is very low. So do you expect, even though the speed is very low, you will see shear there?
Well, shear appears there, even if the solar wind speed is low. It definitely appears. I mean, it just means that the azimuthal velocity will increase a bit within the first, below the Alphen point, and up to a certain height, the azimuthal velocity of the wind will increase at the same time, not at the same rate exactly, but as the wind is accelerated as well. So you have small meridional wind speeds, but you also have smallish but significant azimuthal velocities there, and so the shear is appearing all the way from the beginning, definitely.
Oh, thank you.
Then what is intriguing is the way that some structures, this one is a very simple one, but how this kind of shearing develops in more complex magnetic topologies.
Thank you.
Oh, you're welcome.
Okay.
I'll stop my share. But of course, if you want to talk about these or ask more questions, please do later on. I think we are all getting a bit tired of all the meetings, but feel free to ask questions anytime. We're happy to reply.
Okay. That's great. Michael, are you ready?
Yeah, I'm here. I'm ready. Oh,
you have the final talk of the session.
Yeah.
So survived. We'll see something a little bit different, but perspective. Thank you.
Yeah. Can you see my screen, right?
Yes.
It's good. Very well. So, I think let's start. Hello, my name is Fridman Mikhail. I'm a third year undergraduate student. Today I would like to tell you about the topic of my research, the midterm forecast of geomagnetic storms with the neural networks application. So, the geomagnetic storms associated with the advent of high-speed geoeffective flows and negative value of interplanetary magnetic component Z. So flows basically divided into two types: coronal mass ejections, ICME, and rotating interaction regions. So the paradigm of all short-term forecasting models is the we visit conditions, particularly ICME-like conditions. Moreover, the fact that we have another source of geomagnetic storms and it dominates the minimum of solar activity is mostly ignored. The quality of the short-term forecast is good. The main reason for its success lies in the delay between the arrival of geomagnetic stream on L1 and the arrival of the signal from spacecraft to Earth. So another situation that the quality of midterm forecast is poor. The reason for this is the current midterm forecasts are based on the same paradigm as the short-term ones. Please note that this is an official report on the website of NOAA for 2012 and 2013 years. So horizontal axis in this table is observations on whether there were storms or not, and vertical is predictions which they made. We are not interested in looking at the cell correct null because we are we are trying to solve the task of predicting the geomagnetic storm, not its absence. Please note that value in the cell heat, the correct predicted storms equals 14, and it is less than 19 missed storms where there was no alert, and much less than 44 false alerts. Also note that these are statistics for solar maximum. And such years ICME prevails, for which these forecasts are mostly designed. Accordingly, for during periods of solar minimum, situation is even worse. This leads us to leads us to conclusion that when we apply methods for short-term from a short-term forecasting to midterm forecasting, they basically do not work well. Yeah. So we need to find the precursors in solar wind itself. This work was carried out quite long ago. It was noted that for 12 hours or more, density increases and it begins a small variation in the ULF range begins. So the precursors were found, but now we know about the nature of these precursors. It's figured out that these ULF variations and the magnetic field variations in solar winds, it's not waves, it's structures, plasmoids and magnetic islands that exists in solar winds that are pushed by gelospheric current sheet. As you can see, this is the vertical cumulative density for 72 hours before the geomagnetic storms. So it was just summed vertically. So in the left plot, the blue line is the sum for geomagnetic storms that are less, the DST index is less than -50 nanotesla, and the red one is for -30 nanotesla. Right plot depicts almost the same picture, but it is not the density itself, it's the average fast Fourier transform energy before storm. So as you can see, we can use these patterns to predict geomagnetic storms. These patterns can be formed by hands, which is quite a difficult task, but you also can use neural networks. Neural networks are complex multi-layer structures of simple elements called artificial neurons. An artificial neuron receives a weighted sum at the input, to which a non-linear actuation function is applied. After combining these artificial neurons into layers, there's some data enters the network. It compares its output data with the value of the target function. In addition, using the backpropagation function, weight errors are recalculated. Thus, the neural network is being trained. Recurrent neural network, unlike the usual one, the classical one, is fed with its own output of the previous step. Due to this, a particular memory effect appears. It's similar when a person reads a line of text. A person does not perceive the entire line of text. Intentionally, he runs through it with his eyes. So the training was conducted on data for 2011 to 2017 years. Data was taken from the A spacecraft. So the DST index was also supplied. So to observe the ULF variation, the first Fourier transform was taken. So on the 75% of entire sample is the training set. Validation ran through in 12.5%, and another 12.5% were testing set. Training was not based on testing was not based on the training data, so it was necessary in order to verify the correction of prediction after training the network. The target function was created within following steps. If in next 24 hours the DST index drops below -13 nanotesla, the value of target function is 1. Otherwise, it equals 0. In other words, we just paint 24 hours before the storm with ones. So the neural network was a recurrent neural network. It was the GRU layer with 64 internal units. The 3 graph columns are storms with sudden commencement. So also yellow indicates the moment a stable neural network alert. Blue indicates the beginning of geomagnetic storms. Our so here is the DST index, and here is the density. The lead time is about 20 hours. So also here is another type. It is the sudden impulse commencement. It is very important that we can predict the both types of geomagnetic storms. And here in the right plot, you can even see that we can predict the geomagnetic storms more than 24 hours. But in the statistics, it's also you can see that. So result. This table is this matrix was built solely on a test set, training set. Training on it did not occur. Every hour, a question was asked: will the DST index drop below -13 nanotesla in next 24 hours? Our forecast has 59% of correct hits when NOAA has 18%. So you can see here are 2 histograms for DST index less than -13 nanotesla, and for the geomagnetic storms that DST index drops down the -15 nanotesla. So you can see we can predict these types of storms at least 10 hours, at least for 10 hours with leading times of at least 10 hours. There are lots of future plans with this forecast. We are going to make a probabilistic forecast. So we am planning to merge it with the short-term forecast so our forecast will be published and used in the same spot. So, and we also plan to predict the minimum of the DST index value. So, summary: the midterm geomagnetic storms forecast was built. It was built using the parameters of density and its variations. the results are really good. We can predict both types of geomagnetic storms, and now system is being tested on real-time data, and most likely will be available online soon. So thank you for your attention.
Thank you, Michael. Questions?
Can I ask?
Yes, of course.
What is the accuracy of your prediction? Did you evaluate the false positives and false negatives compared to the real ones?
Yeah.
So I beg your pardon. Could you repeat, please?
What is
Таблицу оправдаемости покажи.
Yeah.
What is the accuracy of your prediction?
So accuracy is not really good for these types of measures, because the most time, mostly there is no geomagnetic storm, and so the main problem with NOAA, they say that, look, we have 400 correct predicted the absence of storm, but they predict correctly less than they miss, and less than they give false alarm a lot. The accuracy is not really good for measuring the quality of the forecast, because here the accuracy would be like about 90%, and it's just does not correctly depict that the situation is really bad. So as you can see, we are not watching at the correct node, and hits are 59% in our forecast, when NOAA has 18.
How can you improve it? Do you see the future? How you can improve it?
We are working on it. Maybe we will add some. My colleagues had our group working of the data set of the current sheets. We could probably add. We are planning to add this data in our network, a neural network.
Okay, thank you.
Yes, we will improve this prognosis. It's like the first kind of the first step, and then we know what we will put on to improve the situation. Yes.
Yeah,
but
we're more
already
likely
better than people do. Okay.
We're more likely in the start of the journey, so.
But to show this, we should to run the prognosis online. So next year, I hope. No, it will be done soon, but next year we will come with a different table, and we will know actually how it works. Thank you. So this is the end, as much how I can see. Well, thanks to everyone. It was a great session and a great meeting, but I hope that next year we will see each other in real. Thank you.
Oh, yes, please.
Yes, please. No, if it depended on me, I would open the borders immediately.
Yeah.
Okay. I wish everyone to be healthy, stay safe. I can say that I got COVID with bad pneumonia, and this is not good. Try to be vaccinated. Okay. Good to see you. Oh, goodbye.
Yeah.
Okay. Bye-bye.
Thank you, Olga.
Thank you for the organizing
Thank you.
the session. Well done.
Thank you.
Thank you. It was nice.